Okay, so we can get started. These are the notes. You guys probably see this at the top. There's a true or false question there. I'm going to give you guys a minute. See if you can answer that true or false question. What does this say? If you have the function of f of x equals whatever on top, blah, 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 over x minus a, then there must be a vertical asymptote at x equals a. So think about that for a minute. Good. So let's say...
That was so funny, Elijah.
That was funny, guys. Okay. Let's say it was x squared minus 9 over x plus 3. Typically, what we do first is factor, right? How does that top factor? Good. X plus 3, x minus 3, it's a difference of squares. So that doesn't always mean that there's going to be a horizontal asymptote, or I'm sorry, a vertical asymptote where the bottom equals 0, just because these cross out. Since these cross out, what shows up there instead of an asymptote? Good, right? So there is a hole at x equals, when you set the bottom equal to 0, it's negative 3. All right, so sometimes there is a vertical asymptote, sometimes there isn't, right? If a factor cancels out, then you get a hole there, not a vertical asymptote. So I'm going to say that this is false. All right, so for this particular function that they give us, let's try to answer the following. Let's find the vertical asymptotes. So again, you don't want to just set the bottom equal to 0 right away. You want to factor it first and see if anything cancels, right? How does the top factor?
So x.
Okay, x plus 4.
Plus 2x.
X minus 2. I don't know what that was. What is the bottom? How does that factor? Okay. Okay, good. X plus 4, x minus 3. Nice, guys. And then you see that x plus 4 cancels out, so you're just left with x minus 2 over x minus 3, right? So there are not two vertical asymptotes here. There's just one. Where is the vertical asymptote here? Good. It's where the bottom equals 0, so x equals 3 is the vertical asymptote. All right. Let's talk about what this means, right? So do you remember what this means? X approaches 3 from the left, right? So this is from the left of f of x, and then number 3 says x approaches 3 from the right. All right. So there's a couple ways that you could think about this. I do think it helps to think about it analytically, kind of, right? So what's a number to the left of 3? Just pick a number. X equals what?
1.
Yeah, let's just say 2, right? Actually, wait, hang on. Let's try 1, right? So let's try x equals... Wait, hang on. Let's just say, yeah, we want to pick one really close to 3. Sorry about that, guys. So let's just say x equals 2.9. When you plug that in there, what do we get? 2.9 minus 2 over 2.9 minus 3. Okay, now what does that become? What kind of number is on top? Okay, there's a positive number, and then on the bottom, what kind of number is that? Negative. So we get a positive over negative. As the numbers get super, super close to 3 from the left, this is going to get you a negative number. So that means at this graph of 3, so this is where 3 is, this is the asymptote, it's going to look something like that, probably, right? It's going to go down. So a couple of days ago, if I had just showed you this graph and I asked you to find the limit, we could just say that it doesn't exist. But now that we are discussing rational functions and asymptotes, we can say that this limit is negative infinity. So we can be more specific with our does not exist. So this limit is negative infinity. All right. What about 3 from the right? What's a number super close to 3 from the right of it? Sure, let's try 3.1. And then when you plug it into the simplified, we get 3.1 minus 2 right? Is that, what is it? Yeah, 3.1 minus 2 over 3.1 minus 3. What kind of number is on top? It's a positive. What kind of number is on the bottom? Also positive, so that means positive over positive is positive. That means the graph of this function at 3 from the right is going to go up towards positive infinity. All right, so if you get a one-sided limit like that at a vertical asymptote, chances are it's going to approach either positive or negative infinity. What if I asked you to find, so let me write this in this space right here, the limit just as x approaches 3 of f of x? Well, from the left, it was going towards negative infinity. From the right, it was going towards positive infinity. So what can we say about this? Just the overall limit. Are they approaching the same direction? This is where we have no other choice but to say does not exist. Right, some rational functions, if you graph them, do approach the same infinity. Like maybe this side goes like that, this side goes like that, and then the limit just is positive infinity. But if they're going in two separate directions, they're approaching two separate infinities. So this is a case where we would say this entire limit does not exist. The other kind of asymptotes that we talked about were horizontal asymptotes. All right, so this is an example of a limit as it's approaching infinity. So for example, ways that you might see that are limits as x approaches infinity, or you might see a limit as x approaches negative infinity. So what's happening as you go further and further to the right and further to the left? We had rules for this. All right, so these are some basic rules for horizontal asymptotes. All right, the first rule is that if the denominator grows bigger, what does that mean as x gets super big? That means you have a number that's not growing as fast, so you get a not as big number on top over a huge number on the bottom. And if you have a not as big number on top and a huge number on the bottom, it's going to get really, really close to 0. Versus if the numerator and the denominator grow equally fast, then you have a really big number, and on the bottom, you have the same really big number. If you have two things that are the same divided each other, that equals 1. All right, finally, if the numerator grows faster than the denominator, then the top is just going to keep growing super, super large. The bottom's not going to grow nearly as fast. This is just going to shoot out towards infinity. All right. Right, so yeah, I think that's fine for now. If you didn't finish it, that's fine. But what you could probably figure out is that ln, when you plug in x equals 1,000, right, you end up with, what is that, 6 point something? Is that 408? Something like that. So ln grows the smallest. All right. The next smallest one, as x gets super, super big, are going to be your polynomial functions. So x to the second, x to the third, and x to the 10th. All right, so we can say that x squared is the 6th one, x to the 3rd is the 5th one, and x to the 10th is 4th. All right, so all your polynomials are growing fast, but they're not as fast as the exponential ones. And if you notice, the exponential ones are going to be ranked 3, 2, and then 1 as you see them. All right, so these are always going to be these are always going to grow the fastest, and ln is always going to grow the slowest. All the polynomials are going to be kind of in between. They're going to grow fast, but not as fast as an exponential function. All right, so at the bottom of this page, I would write this, that your slowest are always going to be an ln of x, maybe a square root of x also. I know that wasn't in here, but a square root, if you remember the graph of a square root, doesn't grow that fast. And then in the middle are going to be your polynomial functions. So polynomial functions meaning x raised to an exponent. So something like x squared, 3x to the 5th, x to the 10th. All of these polynomial functions are going to grow fast, but not as fast as the fastest of these functions, which is an exponential. So exponential functions are always going to grow the fastest. So for example, e to the x, the 4 to the x that you saw right there, are always going to grow the fastest, right? As x is pretty small, they might not look like they're going to grow super differently, but then as x gets really big, then you can kind of see that the exponentials really take off. All right, so something like this is kind of a general rule of thumb that we go by when determining these growth rates. Okay, let's start with this. Let's find the horizontal asymptotes of each function. Again, what this means is just as x gets super, super large. So if you look at number 4, we're going to look at whatever has the highest exponent. And you're always going to do that if you have a polynomial over a polynomial. So if you look at the top, what's the highest exponent that you see there? Okay, so we see an x squared. I'm just going to circle that for now. Bless you. And then what's the highest exponent on the bottom? 1, right? So I'm going to circle whatever has that, right? For the sake of this lesson, you guys can ignore everything else. I don't need it. Between x squared and 3x, what do you think grows faster? Definitely the x squared. When you square a number, it's going to grow super fast. So the top is going to grow fast over something that's slower. So as x gets super, super big, what happens to y? Y is also going to get pretty big, right? Because you have something on top growing super fast versus something on the bottom growing super slow. This one has no horizontal asymptote. This one actually has a slant asymptote, if you remember that. But we're not really going to deal with those too much. All right. Let's think about the next one, right? What's our highest exponent on top? 1. So I'm going to circle whatever has that, right? What about the bottom? All right. How does the top and the bottom compare? And how they grow, right? They grow equally fast. If they grow equally fast, this is where the rule comes from, where you can only look at the leading coefficients, right? If the top and the bottom grow equally fast, again, I don't need this part of it. All right. So then since the top and the bottom are going to grow equally fast, we have a horizontal asymptote at y equals, it's going to be 1/3. We're looking at the coefficient in front of whatever is growing. So it's 1 on top, 3 on the bottom. All right, when you look at number 6, what's the highest exponent on top? 1, right? So I'm going to circle that one. What's the highest exponent on the bottom?
2.
Good, so I'm going to circle that one. Again, you don't need anything else because we're only comparing how fast they're growing. What grows faster, the top or the bottom? The bottom, right? So you're going to have something small over something that grows super huge, right? If you take a small number and divide it by a really, really big number, what number does it get really close to? 0, right? So that means your horizontal asymptote here is going to be at y equals 0. All right, are you okay with that? All right, what about weird ones like this? The square root of x squared. Once again, you're only going to look at the highest exponent which on the top, if you do the square root of x squared, what does that get you? It gets you x. Would it just be x like that? What kind of x values? These would strictly be the positive ones. So this might be new to you guys. You have to denote it as the absolute value of x. When you take the square root of an x squared, the actual value that you get is just going to be the absolute value of that number. So like if you had -2 squared under a radical, you're going to do -2 squared first. So then that's the square root of 4, but the square root of 4 is not going to be plus or minus, that's just going to be 2. So that's why that happens. All right, so we get the square root of x, and then we're also, again, we don't need these constants. I'm only looking at whatever's growing the fastest. And on the bottom, the x is growing the fastest. So what happens first as x approaches infinity? What kind of numbers are on top when you do the absolute value? Right, they're always going to be positive. And as x is approaching positive infinity, what kind of numbers are on the bottom? Positive infinity? They're also positive. So you get positive over positive, which is positive. And then x divided by x is just going to get you 1. But what happens as x approaches negative infinity? As x approaches negative infinity, absolute value of negative is what? Still positive, right? So this is positive on top. And then if x is negative, it's just going to be negative on the bottom. So then this is going to get you positive over negative, which is going to get you -1. Okay, so again, I'm going to do these examples with you guys. When you look at the top of this particular function, what's the highest exponent that takes priority here? The x squared, right? So I'm going to only look at the square root of 4x squared. I'm going to ignore everything else because it's not growing as fast. All right, what about the bottom? What takes priority there? The 3x, right? The exponent of 1. Again, I'm not going to look at anything else. What did we just say about the square root of a variable? That's going to get you what? The absolute value. So we can say that this is the same as the limit as x approaches infinity. What's the square root of 4? 2. And then x squared, square root of that is going to be the absolute value of x over 3x. Even though x is in an absolute value, you can still compare how they grow, right? How does this x compare to this x? Are they growing the same? Yeah, right? They're growing the same, so what do we look at? The coefficients. And since it's approaching positive infinity, we have a positive over a positive, which is just positive, so this limit is 2/3. Okay, that's what we're going to do in the next example, right? This one's approaching positive infinity. So we're saying as x gets really, really big in the positive direction, so that way. All right, but that was a good point, right? Because if we look at number 8, this is the limit as x approaches negative infinity. So what direction are we looking at now? The left-hand side. We're looking as the graph goes that way. But it's going to be the same process, right? What takes priority on top? The x squared. So the square root of x squared, you can ignore everything else. And then the bottom, the same thing. The 3x takes priority, you can ignore everything else. This is going to be the exact same thing as it was in the previous example. So this is the limit as x approaches negative infinity of 2 absolute value of x over 3x. And then still you can compare the growth rates. How does that x compare to that x? Are they growing equally fast? Yes, they are. The only difference is that we're going to negative infinity. So what's the sign on top? Positive. What's the sign on bottom? Negative. You're still looking at your coefficients, but since it's positive over negative, it's going to be what? Negative 2/3. Nice, guys. All right, so super important distinction between those two problems. Are you okay with that, guys? Nice. All right. Let's look at what happens in number 9. There's nothing super special about this one. This is just a normal as x approaches infinity. But where is x here? Okay, it's in the exponent of e. More specifically, it's in the denominator, right? So this is going to be the same as negative 4e to the 1 over. As x gets super, super large, this is 1 over a huge number. And what did we say earlier about 1 over a huge number? What does that get close to? 0. So this is the same as negative 4e to the 0. And then what's e to the 0? This is 1, right? So this limit is just negative 4. All right, what about number 10? What do we know about negative exponents? Anything at all? Very good, right? So this is going to be the limit as x approaches infinity. 5 is going to stay on top, but remember, a negative exponent is going to move to the bottom. So this is 5 over e to the x. So think about it. X is getting really, really big. This is what this means. X approaches infinity. So how do the growth rates compare? 5 doesn't change at all. But what about e to the x? Is that growing? Yeah, right? This is going to be 5 over. When x approaches infinity, what happens to e to the x?
Huge.
Yeah. You get 5 over a huge number. And 5 over a huge number gets really close to what? 0. So this limit is 0. All right, are you okay with that, guys? Okay, but we can continue. So if you have certain trig limits, right? There are some trig limits that we need to use the squeeze theorem, which is at the very bottom here, which I'll talk about in a minute. But there are some that you can kind of think in terms of the rate of change and how fast functions are growing. When you think about something like sine and x, what does the graph of sine look like? Do you guys remember what that looks like? It just goes up and down, up and down, up and down, right? So sine on top is going up and down, up and down, up and down. How does x move? Do you think x moves faster than that? Probably, yeah, right? Because even though x is not a fast function at all, it looks something like that. It grows pretty fast. So it looks something like that versus this that stays constant forever and ever and ever. When x gets really hugely negative and this on top stays the same number or between the same numbers every single time, where do you think this limit is approaching? If this is getting hugely negative over something that doesn't change, good. So this limit's going to approach 0. Right? Remember, huge on the bottom and something not as big on top is always going to get you a limit equal to 0. All right, let's try something similar with this next one. I have negative 3 times cosine of this. Right? So we have 1 over x inside of our cosine. This is the limit as x approaches positive infinity. So if you were to make this bottom really, really big, what, bless you, what does it approach on the inside here? Like what is this entire thing on the inside? Get really close to it. It gets really close to 0. So from here, this is the same as negative 3 times cosine of 0. All right, because it gets really, really close to 0. For the sake of this class, you should know some basic sine and cosine values. You don't need to know for now the entire unit circle, but hopefully we know cosine of 0. Do we know cosine of 0? 1. So this is negative 3 times 1, so negative 3. All right, what about just plain sine? right? So this is going to get really, really big, but we already know that the sine graph looks something like this, right? It's just going to go up and down, up and down, up and down. Do we think it's going to approach any one singular value, even though it's not going hugely large or up or down, right? It's still going to not approach a single value, even though it's bounded between 1 up here and -1 down here. It's not going to approach one singular value. So this limit, we don't even have to say infinity, negative infinity. It's just not going to exist. All right, similar story with cosine, right? We know that cosine of x, this limit by itself does not exist, right? This 5x is going to approach, if it was by itself, it would approach just positive infinity. It would go forever and ever up. But remember, cosine goes between -1 and 1. So that means this graph, if you were to graph it, would be like some crazy oscillation. It would go up, and then way down, something like that. So if this cosine does not exist, then this entire limit does not exist. All right, so for the sake of this particular lesson, you kind of have to understand how these graphs look, how these functions behave. All right, there's not a whole lot of numbers and plugging things in. You kind of just have to understand how the functions behave. All right, very last part of these notes, we're going to talk about something called the squeeze theorem. All right, might also hear sandwich theorem, pinching theorem. But it just means if you have 3 functions, let's say this one is f of x, this one on the outside is h of x, and we have that g of x is in between them, and you have the limit as the limit of f of x is equal to some number. I'm going to call it L for limit. And if this limit of h of x also approaches L, since g is in between those 2 functions, then this limit also has to equal L. Right? It might not make a ton of sense just in technical language like that, but I'll use the next example to show you guys how this would work. All right, so for the sake of this class, I still haven't decided if I'm going to put this on your quiz or not. If I do, I'll tell you, use the squeeze theorem.
When is the quiz?
All right. But I'm going to show you what that would look like in this example here. So we want to use the squeeze theorem to evaluate this limit. Right? It looks like it would behave, we don't really know how it would behave, actually. But there are certain things that we do know about cosine that can help us to solve this limit. First, what do we know about cosine in terms of what kind of values do you get out of cosine? Where do they usually fall? Between what 2 numbers? Yeah, right, 1 and -1. So I know that cosine of this, it doesn't matter what's inside of here, it's always going to get you numbers between 1 and -1. So I'm going to make this little inequality, I'm going to set it up something like this. Do you guys agree with this statement, right? -1 is less than cosine is less than 1. Right? It's always going to be between those 2 values.
It's going to be always between 1 and u.
All right? But we're not trying to find just the limit of this function. We're trying to find the limit of this function times x squared. All right? So if I want to find the limit of this function times x squared, I'm just going to multiply x squared to every single part of this inequality. Right? Might not make a ton of sense right now, just stick with it. And when you do that, when you simplify it, you end up with something like -x squared is less than or equal to cosine of 1 over x squared is less than or equal to x squared. So we get this in a, oh, sorry, I forgot this one, x squared. So x squared cosine of 1 over x squared. All right, so we end up with something like this right now. Do you guys agree with that statement? All right, so if in purple was the original, In green, I just multiplied the entire inequality by x squared. Now you're probably thinking, why does that help you? Well, because now I know this function is between two functions that are a little bit easier to plug numbers into. If I wanted to find the limit as x approaches 0 of this function, right? So let's do the limit as x approaches 0 of negative x squared. What does that equal to? Yeah, right, you're just plugging in, right? There's nothing special with that one. It's just direct substitution. This limit is equal to 0. What about this one? If I did the limit as x approaches 0 of just regular x squared, that is also 0. Do we see that this function now, if we take that limit, so the limit as x approaches 0 of x squared times cosine of 1 over x squared is between this number, 0, and this number, 0. All right? So if it's between 0 and 0, what do you think this limit is? 0. So this limit equals 0, and we're going to say by squeeze theorem. Right, so squeeze theorem we typically do with cosine and sine functions, the ones that go up and down, up and down, up and down. And there's usually going to be a number or another part of the function multiplied to it. And I would tell you guys use squeeze theorem to evaluate, and that's how you know that you have to make this little inequality to kind of bound it between two values and things like that.